Okay, so in the last lecture we talked about how we can convert a second-order differential equation to two first-order differential equations. We looked at a pendulum problem. We converted a problem into two first-order differential equations in terms of theta and theta dot. So in this video, we're going to see how we can use this differential equation to see if any of the methods we've done so far, let's say the forward Euler is going to be stable or unstable, to solve this problem. Okay, so the approach is the following. We have to first, this is nonlinear equation, so we have to first linearize it. And by linearization, that means we have to follow a general definition of a linearization of a function with respect to two variables. Let's say we have a t and y, two variables, and f is a function of these two. Okay, and we want to approximate, let's say, the function at t naught plus delta t and y naught plus delta y, okay, about t naught and y naught. This is basically using Taylor series of a vector function. Okay, so you can think of f as a vector function. And we're going to use the Taylor series about the point of t naught and y naught, where y naught is also a vector. Okay, so our y naught in this problem includes the angle and the angular velocity theta dot. So according to Taylor series, the function f, which is a function of two variables, can be written as the function at point t naught y naught plus delta t times the partial derivative of f with respect to the first variable t, okay, evaluated at t naught, and then plus delta y times partial derivative of f with respect to y at y equal y naught. Okay, so this is a linearized form of f around point t naught and y naught. Okay, so now we can write dy dt right now as d delta y dt, okay, equals this f evaluated at t naught y naught, so in our case is going to be theta naught, which means the initial angle. There's no t here, unfortunately. Okay, plus now the partial derivative of f with respect to t is going to be 0 because we do not have any t in our differential equation. Right? This is f, there's no t in the first element, there's no t in the second element. So derivative of that with respect to t is going to be 0, with respect to t is going to be 0, so you get both zeros here. Right, fine, times delta t, and then plus now delta y, which is going to be delta theta and delta theta naught, right? So this whole vector is going to be delta y, and then times the partial derivative of f with respect to y. Well, we know that y has two elements, theta and theta naught, so the first row of this partial derivative is going to be the partial derivative with respect to theta, partial derivative of the first element with respect to theta naught. And then the second row is going to be partial derivative of the second row here with respect to theta and with respect to theta naught. So by doing the derivatives, we find that this f partial derivative of f with respect to y is going to be this matrix. Okay, this is nothing but a Jacobian with respect to theta and theta naught. Okay, so basically theta and theta naught right here. All right, so we're going to see if, let's say, forward Euler is stable if we use forward Euler to solve this differential equations numerically. Okay, so all we need to do now is to find the eigenvalues of this matrix and check the eigenvalues against the condition for forward Euler, the stability condition. Okay, so the eigenvalues of this matrix at initial angle, which is, let's say, theta equal, let's say 30 degrees, that means we move the pendulum 30 degrees up and then let it go from there. Okay, so the initial theta is going to be 30, or let's say 60. I think I did 60 here, yeah. Okay, So by doing so, by assuming theta naught initially is 60 degrees, we can go ahead and find the eigenvalues of this matrix when theta is equal to 60 degrees and theta naught is 0. So initially there is no initial velocity, so theta naught is going to be 0, so we get 2 zeros here, there's 1 here, and then cos of 60 degrees is going to be 1/2. Okay, so the eigenvalues for this matrix is going to be lambda squared, and then plus 1/2 is equal to 0. Okay, and if you solve for the lambda, now it's going to have 2 eigenvalues. So the eigenvalue is going to be plus minus square root of 1/2 times I, which is the root of the square root of the that's the imaginary number, which is the square root of -1. Okay, so we have 2 lambdas for an initial angle of 60 degrees. I'm going to go ahead and locate these 2 lambdas on the complex plane. So this is imaginary part of lambda del x, and this is the real part. This is the real part of lambda del x. This is the imaginary part of lambda del x. And so for imaginary part, we have plus minus square root of 2 divided by 2. So the 2 points on the y-axis. By the way, so this lambda 1, lambda 2, these are the eigenvalues of the matrix, and they're basically they're actually the lambda times the x, not really the lambda. So although I have lambda here, but this lambda 1 means lambda 1 times the x, and this means lambda 2 times the x. Okay, that's why we actually locate them on this plane, which is the real and imaginary part of lambda del x. Okay. So because the 2 eigenvalues are outside of the unit circle for forward Euler, this method is unconditionally unstable if we do not consider any damping. So if the damping is 0, like beta is 0, then the eigenvalues for this matrix is going to be these 2, and these 2 are outside of the unit circle for forward Euler. That means the method is unconditionally stable, and the method is going to diverge over a long time. However, if we add friction or the drag with the air, again, if we add the friction between the pendulum and the air to the problem, then there's a chance that the lambda, the 2 lambdas that we find the eigenvalues, now this time sit inside this circle, okay, for which then the problem is not going to be unstable anymore, so it's going to be conditionally stable. But that depends on how much the beta is. Depending on the beta, we can actually have these 2 come over the circle, or basically still stay outside the circle. Anyway, so without beta, for sure, this is outside, or these 2 are outside the circle, and the method is going to be unstable. So in general, if we can convert our differential equations to something like this, dy dt equals some matrix times y, well, now we're talking about the vector equation, right? So some matrix A times y, and then plus some other function of t, then the eigenvalues of this A, okay, now A is constant, the eigenvalues of this A will show whether the method is going to be stable or not. Okay, so if the eigenvalues of A, both eigenvalues, are within the stability region, then we're going to call the method as stable. Okay, but if one of the lambdas, at least one of the lambdas, falls outside the stability region, then the method is going to be unstable anyways. Okay, so for instability, at least one lambda I, one eigenvalue of A needs to be outside the circle, or outside the stability region, and for stability, all lambdas, all eigenvalues need to be inside the stability region. Okay, so that's how we can basically decide whether the method is stable or unstable for every problem by linearizing the problem, looking at the eigenvalues of the coefficient matrix, and decide whether the method is going to be stable or not. Okay. So this A that we talked about here is nothing but the Jacobian of f. Okay, and the Jacobian of f are, or the Jacobian of f actually includes the partial derivative of f with respect to all the unknowns. If you have like, n elements in y, then the Jacobian is going to be n rows and n columns. And for every element, we're going to calculate the partial derivative of the, let's say, ith element of f with respect to jth element of y. Okay, so this is a generic form of the element ij of the Jacobian. And once we find the Jacobian, then we can go ahead and find the eigenvalues. Okay? All right, I think this sort of explains how we can analyze the stability of the pendulum problem. Now, if you really want to solve the pendulum problem using, let's say, forward Euler, then after we convert the problem into first order differential equations like that, then we can go ahead and write the forward Euler discretized equation for this differential equation. Like on the left side of the discretized equation, we're going to have y plus 1 minus yi divided by del t, but now the y's are a vector. And on the right side, we have f of t and yi. Again, f is a vector. Because everything is vector, then we can solve for y plus 1 with one equation like that. We can iterate over this and find yi. So that's for forward Euler. For RK4, we can do the same thing. Now this time we have 4 k values, but that's fine. All of the f's are vectors, and inside the f we have the t, the first independent variable, and then the y. Again, y is going to be the vector. So then k2 is going to be t plus delta t over 2, and then on the y side we're going to have yi as a vector, like that's in ith iteration, plus k1, which is again the vector we found before, times delta t over 2. Again, this f is a vector, and it's nothing but this right side of the differential equation after we convert it into two first order differential equations. Alright, so we can find k1 all the way to k4 similarly, and then the y plus 1 is going to be the weighted sum of the k's. I think this is very similar to the scalar version. The only thing is the k here is a vector. Or all the k's actually, k1 to k4, all of them are vector. Okay, now backward Euler is a little bit more involved, because in backward Euler, although the left side is I plus 1 minus yi, the right side is actually t and yi plus 1. Okay, so we're going to plug in f in here from there. So this is f. We're going to plug in terms of the yi plus 1, and at the end of the day we get yi plus 1 from the left side minus delta t times f from the right side, which actually now brought to the left side. Okay, and then minus yi equal to 0. Now this is an implicit equation we have to solve for yi plus 1. If you open this up, y plus 1 is nothing but the first element of it, which is theta I plus 1 and theta naught, or sorry, theta dot I plus 1. Okay, put them in here, and then minus delta t there. The f is going to be evaluated at I plus 1, so it's going to be theta dot I plus 1 minus sine of theta I plus 1 minus beta theta dot I plus 1, absolute value of theta dot I plus 1. Okay, so that's this piece, and then minus yi, which is going to be theta dot I, and that's equal to vector 0. Okay, the goal here is we have to solve for the highest index variables, which means theta I plus 1 and theta dot I plus 1. Okay, all right. So now you see that this is a nonlinear equation in terms of the theta and theta dot. Okay. Again, theta I plus 1 and theta dot I plus 1. So we have to use Newton's method to solve for the theta I plus 1 and theta dot I plus 1, similar to the nonlinear differential equation we had before. So stay tuned for the next video on how we can solve this nonlinear differential equation for theta I plus 1 and theta dot I plus 1. Thank you so much for watching.